Welcome, my friends. In this video, I'll be covering section 8.7, the confidence interval for independent data. For this confidence interval, we want to estimate how much larger, or smaller, one mean is compared to another for independent populations. For example, consider the variable, the weekly screen time use for either Gen Z, population mean 1, or millennials, population mean 2. We are trying to estimate mu1 minus mu2, which represents how many more hours Gen Z spends on screens per week compared to millennials on average, or less time if the result is negative. For example, consider this possible 95% confidence interval, which ranges from 5 to 15. This would mean that we are 95% sure that Gen Z spends anywhere from 5 to 15 more hours per week on average on screens than millennials. We use more because the numbers are positive. Or we could have negative numbers, perhaps from -10 to -5. That would mean that we are 95% sure that Gen Z spends anywhere from 5 to 10 less hours per week on average on screens than millennials. We say less because the numbers are negative. Here's the confidence interval to estimate the difference in population means. Due to the calculation-intensive nature of this formula, we will be using the TI-84 calculator function called 2SAMPTINT to calculate the confidence interval for us. On a number line, the confidence interval will look something like this. We have the difference in sample means, which is our point estimate, at the middle of the confidence interval. Then we're adding and subtracting the margin of error, which is everything after the plus or minus in the formula, and then we will get to our upper bound and our lower bound. We will be 95% confident, or whatever our confidence level is, that the true difference in population means falls between the lower and upper bound. We will only be completing the confidence interval for independent data as a post hoc for the independent t-test in this class, and we will only do it when the null hypothesis is rejected. This confidence interval will answer the question, which mean is bigger, and by how much? We will be using the FRED technique to complete this confidence interval. The F in FRED stands for formulate the problem. We will be skipping this step because it was completed as part of the independent t-test. The R stands for review conditions. Once again, we will be skipping this step because it was already completed as part of the independent t-test. For E, we have execute calculations, in which we will be using the 2SAMPTINT function on the TI-84 calculator. As far as drawing conclusions, we will be using the same template that we have used in other confidence intervals. We are C% confident that population mean 1 is anywhere from the lower bound to the upper bound either larger or smaller than the second population mean. We will always use the positive versions of the lower and upper bounds because the word either larger or smaller will be dealing with the possible positive versus negative sign. All right, here's the same example that we used in the previous video to do our independent t-test, which we will now use to do a confidence interval. Grand Valley instructor Luke Ellison, which is me, wants to test to see if his students are performing better in Stat 215 than his rival instructor Lauren Berry. Luke and Lauren each decide to give the same exact final exam to their students and compare the results. And then they give us all the information here. I'm not going to read through that again. Estimate the difference between the two means using a 90% confidence interval. So just like last time, I'm going to go ahead and write out the information. We had a sample size of 108 for Luke. The sample mean was 79.02 with a standard deviation of 18.88. The sample size for Lauren is 78. The sample mean was 74, and the standard deviation is 21.97, the exact same information we used in the previous video. As far as executing calculations, we're going to be using the TI-84 calculator. So let's grab that. And I'm going to go ahead and go to the 2SAMPT interval function, which is in the same place as the 2SAMPT test. So I can go back to stat, arrow to tests, and I can scroll down and scroll past the 2SAMPT test and scroll down, and I will eventually find the 2SAMPTINT. And then I can enter stats here. If I had data, I could click data, and then I could have the information from the lists. But in this case, I just have stats. So that's what I'm going to use. And I'm going to go down here, and I'm going to change the confidence level to 0.90 for a 90% confidence interval. I'm always going to select no for pooled. Selecting no means that we are not assuming the population standard deviations are equal. And then we can go ahead and calculate. We will always select no. And here we have our confidence interval, and I have that same output here on the slide. So it's going to give us a number of different things. It's going to spit back a lot of the numbers that we kind of entered in, or if you entered in data, it would calculate the means and standard deviations for you. It's going to give us the degrees of freedom, which we don't need for the way that we're doing this test, but we will just need the lower and upper bounds to our confidence interval. Okay, at this point, we are ready to draw our conclusions. And we kind of got an interesting result here, which doesn't happen too often with the way that we're doing this in class. We actually have a negative number for our lower bound and a positive number for the upper bound. This is a fairly rare case, and the only reason we ended up getting this is because we rejected the null hypothesis, as you might remember, but not significantly. The p-value was not all that low, which meant that we were able to conclude there was a difference between them, but not a large difference, you might say. And that's what's resulting in this kind of a split in signs here. So as you might remember, the negatives represent basically smaller at the first population, and the positives represent higher at the first population. So we kind of have mixed signals here. But anyways, this is the way that I wrote the conclusion. Using the template, I said we are 90% confident that the mean final exam score for all possible students taking Luke's class is anywhere from, and now I kind of distributed that, usually it says higher or lower. The lower is kind of applying to this 0.0782 number, and the higher is applying to this 10.118. So we kind of have the mixed signals. It could be anywhere. It could be a little bit lower for Luke's class, or it could be all the way up to about 10 higher for Luke's class, right? As compared to the mean final exam score for all possible students taking Lauren's class. So it takes a little bit of detail and attention to the detail here to write the conclusion here, but hopefully this makes sense based on what we got. Okay, so here is an example for you to try, which is also based on the same information that was in the last video for the extra question. So among music majors, do pianists or violinists practice more hours per week? The weekly practice time from a random sample of 12 piano performance majors and 9 violin performance majors is shown below at XYZ University, I think is what they said in the last video. Construct a 90% confidence interval for the difference in the means of these two populations. So all you have to do is the last two steps here. So in this case, you'll have to plug those numbers into your calculator, and then you will run the 2samp tint, and then go ahead and try to write a conclusion from that as well. All right, so that's all I had to talk about in this video, so I will see you in the next one.